Alright, silly people, here's the situation. We have a uniform hoop of mass m that is rolling around on top of a cylinder with a fixed radius, big R. Um, the hoop is rolling without slipping, and we have to use the method of Lagrange multipliers to find the angle theta where the hoop falls off of the cylinder and rolls away. Uh, so when you're doing Lagrange multipliers, you have to find forces of constraint. So, and usually the forces of constraint are just given by like the geometry of the problem. So the first constraint that we have, which I'm going to call F1, is that whenever the hoop is still on the cylinder, that the radial distance from the center of the cylinder to the center of the hoop is constant. That is rho, I'm going to call it rho, is equal to r plus r. And then to put it in the form of an actual constraint equation, you have to have 0 on one side. So it's going to be rho minus r is equal to 0. With the constraint that rho dot is equal to 0. Okay. Next equation of constraint, F2. It's given that the hoop is rolling without slipping. Okay. So what that turns into is the radial distance times theta dot, which is the linear velocity of the hoop with respect to theta, is equal to phi dot minus theta dot times little r, which again can be it can be interpreted as a linear velocity with respect to phi and theta. If you want to put this in terms of an actual constraint equation, I'm going to call it plus r times theta dot minus phi dot is equal to 0. Normally, equations of constraint are in terms of coordinates rather than time derivatives of coordinates. So it's really useful at this point to just say that r theta plus little r theta minus phi is an equivalent constraint condition. Just taking the time integral of that gives you that, and we can actually use that when we're solving the problem. Okay, we have constraint equations. Let's now do the Lagrangian. So kinetic energy, we're not going to apply any of the constraints until we've fully written the Lagrangian and solved the Euler-Lagrange equation with respect to each coordinate. So we have to write every kinetic energy term, which means there's going to be one which is a rotational kinetic energy for the hoop. So mr squared phi dot squared. There's going to be one where rho is allowed to change, so rho dot squared. There's going to be one where theta is allowed to change, so rho squared theta dot squared. That's your kinetic energy. And then the potential energy, as usual, is given by mgh, the height of the hoop, which in our coordinate definitions is mg cosine. It's mg rho cosine theta. So our whole Lagrangian is m over 2 r squared phi dot squared plus rho dot squared plus rho squared theta dot squared minus mg rho cos theta. All right. Now we need to now solve the Euler-Lagrange equation for each coordinate independently. We'll start with rho. Q equals rho. So del L del rho dot is just m rho dot, the time derivative of which will be m rho 2 dots, and then the partial of the Lagrangian with respect to just rho is m rho squared, nope, it's m rho theta dot squared minus mg cosine theta. So the Euler-Lagrange equation will read m rho 2 dots plus mg cosine theta minus m rho theta dot squared on the left hand side, and on the right hand side we have to have a generalized force. We're dealing with constraints, so the generalized forces aren't zero. That's going to be q rho. Generally, generalized forces are just given by the sum over I lambda I del F del Qj, del Fi del Qj. So looking at our particular equations of constraint, q rho then will be lambda 1 del F1 del rho plus lambda 2 del F2 del rho. Our first equation of constraint did actually depend on rho. The second one did not. So we can write q rho as just being equal to lambda 1. Yeah. Rewriting the equation of motion then, m rho 2 dots plus mg cos theta minus m rho theta dot squared minus lambda 1 is equal to 0. Very cool. Now we can look at theta and do a very similar thing. So I've got the Lagrangian up here as well. So del L del theta dot is going to be m rho squared theta dot. Okay, and then taking the partial derivative of the Lagrangian now with respect to theta, it's going to be mg rho sine theta. And then if you take the time derivative of the partial with respect to theta dot, you get something gross. So it's going to be 2m rho dot theta dot plus m rho squared theta 2 dots. We'll also need the generalized force q theta, which will be lambda 1 del F1 del theta plus lambda 2 del F2 del theta. Now it's pretty cool that that F1 doesn't depend on theta. F2 does though, which was just r plus r. So it's going to be q theta is equal to lambda 2 r plus r, right? Cool. Let's throw that into the mix. So we have a Euler-Lagrange equation that will read 2m rho dot theta dot plus m rho squared theta 2 dots minus mg rho sine theta minus lambda 2 r plus r is equal to 0. All right. Moving on to phi. I swear every part of this is necessary. Moving on to phi. Del L del phi dot will be mr squared phi dot, and then taking the time derivative of that, oh my goodness, I need to write this correctly. That's going to be 2mr dot phi dot plus mr squared phi 2 dots. All right. And then, interestingly, the Lagrangian doesn't explicitly depend on just phi, so that's 0. Then our Euler-Lagrange, we need to calculate q phi. Lambda 1 del f1 del phi plus lambda 2 del f2 del phi. Now, f1 didn't depend on phi, f2 did. The partial derivative will be minus r. Q phi equals minus r lambda 2. Okay. Now we can write our third equation of motion. So mr squared phi 2 dots plus 2m r dot phi dot minus, or plus actually, r lambda 2 is equal to 0. Okay. Now we have our three equations of motion, and we're going to pretty much work backwards to try and find the actual value for lambda 1, and then use that to find the angle that the hoop falls off. This is where we can actually start applying our constraints throughout the problem. Solving the f2 for phi, you'll have that phi dot, solving the equation for phi, you just have theta times r plus r over little r, which when you take the time derivative of those, just kind of keeps the same form for both of them. And we can use that to rewrite this equation in terms of theta. The second term will actually go away because r dot is 0. So you'll have mr squared times theta 2 dots r plus r over little r plus r lambda 2 is equal to 0. We can use this to solve for lambda 2. So you'll get m theta 2 dots times r plus r is equal to minus lambda 2. I'm actually going to throw the minus sign onto the other side. And then we can plug that into our second equation of motion, which I've gotten so far away that couldn't see it anymore. It's this stuff here. So applying equations of constraint throughout, now we're doing rho dot is equal to 0, so the first term will go away. You'll get m rho squared theta 2 dots minus mg rho sine theta plus lambda 2 r plus r squared times theta dot m theta dot 2 dots is 0. Okay. Now, remember the definition of rho is that it's exactly equal to r plus r. So we can now plug that in to this and then collect terms. So you'll actually have 2 factors of m rho squared times theta 2 dots minus mg rho sine theta is equal to 0. This is a differential equation that we will solve. Canceling out factors of m, it's just g sine theta over 2 rho. So, this is going to be silly. We're going to use the fact that the time derivative of theta dot squared is equal to 2 theta 2 dots to solve for this. Okay. So just plugging in what we got for theta 2 dots, you have the time derivative of theta dot squared is equal to 2 theta dots times g sine alpha over 2 rho. Turning this into an integral, you'll have theta dot squared is equal to, the 2's will cancel out, so you'll just have g sine theta. It's an integral divided by rho. Theta dot is just d theta dt, so you're doing d theta dt times dt, and those dt's will cancel out, so you just have g sine theta over rho d theta, which isn't too bad of an integral. So you're just doing theta dot squared is just minus g cosine theta over rho plus some integration constant. Don't forget the integration constant, which we can also solve for, because we know that the hoop is starting at rest when it's at the top of the cylinder. So theta dot will actually be 0 when theta is 0. Right, so just plugging that guy in, we have minus g over rho plus c, so c is just g over rho. So finally we have a form for theta dot squared as being g over rho times 1 minus cosine theta. Fantastic. We had a theta dot squared term in our first equation of motion, which we will finally get back to. Now we're really far away from it. It's this guy here. Boop. Cool. So it looks like we have a rho 2 dots term, which will go away because rho is a constant. So you'll have the first term, mg cosine theta minus m rho times g over rho times 1 minus cosine theta is equal to lambda 1. Okay, let's just start simplifying that. So we'll have mg cosine theta minus mg plus mg cosine theta. So 2 factors of mg cosine theta minus mg. So to put it in simplest terms, lambda 1 is equal to mg 2 cosine theta minus 1. All right. That's your Lagrange multiplier. So the constraint force will stop being applied whenever the system goes out of like the geometric state that we required, which was that the hoop is actually staying on the cylinder. So this constraint force will entirely go away whenever at the exact moment where theta is at the point where it's falling off. What I'm saying is that 0 is equal to mg 2 cosine theta max minus 1. So theta max is going to be the angle where it falls off. Which means we can get rid of the mg. We just have the 1/2 is equal to cosine theta max. So arc cosine of 1/2 equals theta max, and that's just pi thirds or 60 degrees. There you go.